The nearest star to our sun is about 4.25 light years away. That is the standard unit of cosmic loneliness, the number cited in every introduction to interstellar space. But here is something that almost never gets mentioned alongside it. Our solar system may already extend more than a third of the way there, not the planets, not Pluto, not even the boundary where the sun's wind stops blowing. The solar system itself, defined by the reach of the sun's gravity, stretches outward to distances that overlap meaningfully with the gap between stars. Every diagram you have ever seen, every classroom poster, every documentary animation, every museum display ends the solar system somewhere around Neptune. A few include Pluto. Almost none include what lies beyond. What lies beyond is not empty space. It is a vast, dark, nearly spherical shell of frozen objects, possibly 1 trillion or more of them, orbiting the sun at distances so extreme that they complete a single orbit once every few million years. Their surfaces hover just a handful of degrees above absolute zero. They receive so little sunlight that the combined glow of distant stars across the galaxy contributes a comparable amount of illumination. They are as remote from the sun as objects can be while still remaining gravitationally bound to it. They are technically inside the solar system. They are the Oort Cloud, and the fact that you almost certainly learned almost nothing about them represents one of the most significant gaps in how science communicates the true architecture of our cosmic neighborhood. To understand what the Oort Cloud actually is, it helps to start from the center and work outward. Not as a refresher, but because the scale only registers if you build it step by step, each layer making the next more astonishing. The sun is a sphere of superheated plasma, roughly 860,000 miles across, burning hydrogen into helium at a core temperature exceeding 27 million degrees Fahrenheit. Every second, it converts approximately 4 million tons of matter into pure energy and radiates that energy outward in every direction. The inner solar system forms within the first few astronomical units of this radiation. 1 astronomical unit is the average distance between Earth and the Sun, approximately 93 million miles. Mercury sits at 4/10 of an astronomical unit, Venus at 7/10, Earth at 1, Mars at roughly 1.5. Light covers the entire inner solar system in under 25 minutes. Past the asteroid belt, which stretches from roughly 2 to 3 astronomical units, the solar system opens into a more expansive realm. Jupiter orbits at 5.2 astronomical units, so massive that it contains more than twice the combined mass of every other planet combined. Saturn follows at 9.5, then Uranus at 19, then Neptune at 30. At Neptune's distance, sunlight is 900 times fainter than it is at Earth. A person standing on its surface would need a telescope just to make out the sun as a disk rather than a bright point of light. The planet takes 165 Earth years to complete a single orbit. Someone born when Neptune was at one position in its orbit would live an entire human lifetime and die before the planet returned to that same position in the sky. This is where every familiar diagram ends. 8 planets, a central star, and a clean fade to black at the outer edge. The implicit message is clear. Solar system concluded. Interstellar space begins. Move along, except the solar system does not end at Neptune. It does not end at Pluto. It does not even end at the boundary where the sun's wind stops blowing. The sun's gravitational reach extends outward for distances so extreme that the entire planetary region, every planet, every moon, every asteroid, every comet currently blazing through inner space, shrinks to less than 0.1% of the sun's total domain. Think about what that means. Everything humanity has ever studied directly, every destination we have ever reached with a spacecraft, every object we have ever photographed up close, represents less than 0.1% of the solar system. The remaining 99.9% consists of frozen darkness that most people have never heard about, and that no instrument has ever directly seen. Beyond Neptune lies the Kuiper Belt, a broad disk of icy bodies extending from roughly 30 to 50 astronomical units. It contains Pluto at 39 astronomical units, along with at least 100,000 objects larger than 60 miles across, and likely millions of smaller ones. Astronomers David Jewett and Jane Liu discovered the first Kuiper Belt object beyond Pluto in 1992, confirming a structure that had been theorized for decades. Sunlight reaches the outer edge of the Kuiper Belt in about 7 hours. Relative to what comes next, it is barely an opening paragraph. Beyond the Kuiper Belt lies the scattered disk, a population of objects in highly elongated orbits flung outward by Neptune's gravity billions of years ago. One of the most extreme known objects in this zone is the dwarf planet Eris, which reaches nearly 97 astronomical units from the Sun at its most distant point. And then there is Sedna. Discovered in 2003 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz, Sedna follows one of the most extraordinary orbits of any known solar system object. Its closest approach to the Sun sits at approximately 76 astronomical units. Its farthest point stretches to roughly 937 astronomical units. Sedna takes approximately 11,400 years to complete a single orbit. It exists in a region too distant to be explained by the Kuiper Belt and too detached from the planets for Neptune's gravity to have put it there. It is a boundary object, a physical artifact pointing unmistakably towards something far larger and more remote than anything in the standard diagram. At roughly 120 astronomical units sits the heliopause. This is the boundary where the solar wind, a torrent of charged particles streaming outward from the Sun at roughly 1 million miles per hour, finally loses its contest against the pressure of the interstellar medium. Beyond this point, interstellar particles and magnetic fields take over. Voyager 1 crossed this boundary in August 2012 at a distance of about 122 astronomical units from the Sun. Voyager 2 followed in November 2018 at approximately 119 astronomical units. Both spacecraft sent back data confirming they had entered interstellar space in the sense that the Sun's outflowing material no longer held sway over their local environment, and this is where the most consequential misunderstanding in modern public science communication occurred when NASA confirmed in September 2013 that Voyager 1 had crossed the heliopause. Headlines around the world declared that humanity's most distant spacecraft had left the solar system. News programs described it as the first human-made object to enter interstellar space. Technically, the phrasing was accurate, but the implication was profoundly misleading. Millions of people absorbed a single takeaway. The solar system ends somewhere around 120 astronomical units. Voyager crossed the line. Story over. The heliopause is not a gravitational boundary. It is a plasma boundary. It marks where the Sun's wind stops, not where the Sun's gravity stops. Gravity reaches incomparably farther than the wind. The Sun still holds objects in orbit at distances that would take Voyager hundreds of centuries to reach. Crossing the heliopause and declaring the solar system finished is roughly like stepping off your front porch and announcing you have left your country. The actual property line is nearly 1,000 times farther away. Something is out there, far beyond the heliopause. Something enormous, ancient, and invisible. The evidence for its existence has been arriving in our skies for as long as humans have tracked the heavens. The messengers are comets, specifically long-period comets. Short-period comets orbit the Sun in predictable cycles, returning every few decades or centuries. Their orbits are relatively compact and tilted only modestly relative to the plane of the planets. Most originate in the Kuiper Belt or the scattered disk, gravitationally nudged inward until they settle into repeating paths. Long-period comets are different. They arrive on orbits that take thousands, tens of thousands, sometimes hundreds of thousands of years to complete. They plunge toward the Sun from enormous distances, swing around it in a blaze of vaporizing ice and gas, then retreat back into the outer darkness on trajectories so elongated they will not return for millennia. Some arrive on their very first visit to the inner solar system, since the planets formed 4.5 billion years ago. Here is what makes them so revealing. Long-period comets do not arrive from one direction. They come from everywhere. Their orbits are tilted at every conceivable angle to the plane of the planets. Some arrive from above that plane, some from below, some from the direction of Orion, others from the opposite side of the sky entirely. If you plotted their most distant orbital points on a three-dimensional map, they would form not a flat disk like the Kuiper Belt, but a sphere. A shell of origin points surrounding the Sun in every direction at distances of tens of thousands of astronomical units. This pattern is not random. It is a signature. It tells scientists that somewhere out there, at distances vastly exceeding anything in the standard solar system diagram, there exists a roughly spherical reservoir of icy objects from which these comets are being dislodged and sent falling toward the Sun. The reservoir must be enormous to produce comets arriving from all directions. It must be distant to explain their orbital periods of thousands and tens of thousands of years. And it must contain a staggering number of objects, because long-period comets keep arriving century after century, and each one that plunges too close to the Sun and evaporates must be replaced by another from the reservoir to sustain the supply across billions of years. In 1950, a Dutch astronomer named Jan Hendrik Oort sat down with the orbital data of 19 long-period comets and noticed something striking. When he calculated their aphelia, the most distant points of their orbits, they clustered around a specific range of distances, roughly 20,000 to 50,000 astronomical units from the Sun. The clustering was too tight to be coincidental. It pointed toward a specific structure at a specific distance, a vast cloud of icy bodies orbiting the Sun at the outermost edge of its gravitational reach. Oort was not the first to propose such a structure. In 1932, Estonian astronomer Ernst Öpik had suggested a similar reservoir, but Oort had the orbital statistics, and he had the insight to connect the observed trajectories of comets with a physical mechanism that could explain how objects in stable, distant orbits occasionally get knocked inward. That mechanism was stellar perturbation. Stars do not stay fixed in the sky. They move through the galaxy on their own orbits, and occasionally, over millions of years, a neighboring star passes relatively close to the Sun, not close enough to disrupt the planets, but close enough to gravitationally nudge objects at the very outer edge of the Sun's influence. Those nudges can alter an icy body's orbit just enough to send it falling inward on a new trajectory, one that eventually carries it past Jupiter, past Mars, past Earth, close enough to the Sun for its ice to vaporize into a glowing tail. A comet is born, and its birth certificate reveals its home address, a region of space so far from the Sun that the boundary between the solar system and the galaxy itself begins to blur. Oort proposed that this reservoir is not a thin ring or flat disk, but a sphere, a thick shell of icy objects surrounding the entire solar system at distances thousands of times greater than Neptune's orbit. The structure was named the Oort Cloud in his honor, and in the decades since his original paper, every new line of evidence has strengthened the case for its existence. Scientists divide the Oort Cloud into two broad regions with distinct characteristics, shaped by different physical forces. The inner region is called the Hills Cloud, named after astronomer Jack Hills, who proposed its existence in 1981. The Hills Cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun and extend outward to roughly 20,000 astronomical units. Unlike the spherical outer region, the Hills Cloud is believed to be more flattened, shaped like a thick torus, concentrated loosely around the plane of the solar system. It is thought to be far denser than the outer cloud, containing perhaps 5 to 10 times as many objects, with some models suggesting tens of billions or even hundreds of billions of icy bodies in this inner zone. Alone, the outer Oort Cloud begins beyond the Hills Cloud and extends outward to somewhere between 50,000 and 100,000 astronomical units from the Sun, with some estimates placing the absolute outer boundary as far as 150,000 to 200,000 astronomical units. This outer shell is approximately spherical. Objects within it orbit the Sun at every inclination and in every direction. Some orbit in the same direction as the planets. Others orbit in the opposite direction. Some trace paths that are nearly circular at tremendous distances. Others follow highly elongated ellipses that carry them from the outer cloud deep into the inner solar system, and back again over orbital periods, measured in millions of years. The total population of the Oort Cloud remains uncertain because you cannot count objects you cannot see, but models based on the observed rate of long-period comet arrivals and the dynamics of how comets are dislodged from the cloud suggest staggering numbers. Conservative estimates place the population at several hundred billion objects larger than about half a mile across. More generous models propose 1 trillion or more. The combined mass of the entire Oort Cloud, despite containing so many objects, is believed to be modest, perhaps a fraction of an Earth mass, to as much as several Earth masses, depending on the model. This may seem modest, but spread across a sphere potentially light years in radius, it means the Oort Cloud is one of the most diffuse structures in the known solar system. The objects themselves are immensely isolated from each other. Those objects are believed to be icy planetesimals, primordial remnants from the formation of the solar system roughly 4.5 billion years ago. They are composed primarily of water ice, along with frozen carbon dioxide, methane, ammonia, and other volatile compounds mixed with dust and rock. Most are small, probably a few miles across or less. though some could be substantially larger. They are dark, reflecting very little sunlight, which is itself vanishingly faint at their enormous distances. A typical Oort Cloud object receives so little solar energy that its surface temperature hovers somewhere around 4 to 10 Kelvin, just a few degrees above absolute zero. At these temperatures, even gases like nitrogen and carbon monoxide are frozen solid. These are the coldest, most isolated objects in the solar system, drifting through near total darkness in orbits that take millions of years to complete. The comets that reach us are their ambassadors. Consider Comet Hale-Bopp, which appeared in 1997 and became one of the most widely observed comets of the 20th century. Its orbital period was calculated at roughly 2,500 years, and its aphelion sits at approximately 370 astronomical units. Hale-Bopp spent thousands of years in the cold outer reaches before gravitational forces redirected it inward, where it briefly became a brilliant spectacle, visible even in daylight before retreating back into the darkness. Then there is Comet Hyakutake, which passed close to Earth in 1996, before its encounter with the inner solar system. Its orbit carried it to an aphelion somewhere in the range of 1,000 to 2,000 astronomical units, placing its most distant point near the threshold of the inner Hills cloud. When Hyakutake last visited the inner solar system, modern humans were still hunting across Ice Age landscapes and painting animals on cave walls. That comet has been traveling through the outer dark ever since, and it is not due back for millennia. More recently, Comet C/2025 R3 Pan-STARRS, discovered in September of 2025 and confirmed by the Minor Planet Center, drew attention as another long-period visitor from the outer solar system. Astronomers classified it as a long-period comet with a steep orbital inclination far above the plane of the planets, exactly the kind of trajectory expected from an Oort Cloud origin. The comet reached perihelion in April of 2026 at a distance of roughly 47 million miles from the Sun. Comets like this one arrive regularly. Each one is a fresh data point confirming that the distant reservoir is still active, still populated, still sending members inward on trajectories. Shaped by galactic tides and stellar encounters across billions of years, understanding where all these icy bodies came from requires rewinding to the solar system's earliest history. Roughly 4.5 billion years ago, at that time, the Sun was surrounded by a massive disk of gas and dust called the protoplanetary disk. Within this disk, solid particles collided and stuck together, gradually building larger and larger objects. The biggest became the cores of the giant planets, Jupiter, Saturn, Uranus, and Neptune. But the disk contained far more solid material than the planets could absorb. Trillions of smaller icy bodies called planetesimals remained as leftovers. As the giant planets grew and migrated through the disk, their powerful gravitational fields scattered these planetesimals in every direction. Jupiter, the most massive, was particularly effective. It flung planetesimals both inward and outward with tremendous force. Many were ejected from the solar system entirely, launched on trajectories that carried them beyond the Sun's gravitational reach and into interstellar space, where they presumably drift still, anonymous wanderers between the stars. But many others were scattered into highly elongated orbits that carried them to enormous distances without quite reaching escape velocity. They remained gravitationally bound to the Sun, orbiting at thousands or tens of thousands of astronomical units on paths that took millions of years to complete. Once these scattered planetesimals reached sufficiently large distances, the galactic tide and the gravitational influence of the Sun's stellar birth cluster began to modify their orbits. The galactic tide gradually raised their perihelion distances, pulling them away from the planetary region and preventing the giant planets from scattering them again. Over hundreds of millions of years, this process decoupled the scattered objects from the planets entirely, trapping them in stable orbits at great distances. They became the Oort Cloud. This formation model, refined through decades of increasingly sophisticated computer simulations, explains several key features of the structure. It explains why the outer cloud is spherical, because the galactic tide randomizes orbital inclinations over time, spreading objects into a shell rather than a disk. It explains why the inner cloud is more flattened, because galactic tidal effects are weaker at shorter distances and have not had enough time to fully randomize the orbits. It explains the total mass, because most scattered planetesimals were ejected entirely with only a fraction remaining bound. And it explains the ongoing comet supply, because the cloud contains enough objects to sustain a steady, trickle of comets over the solar system's entire lifetime without being depleted. The formation model is closely tied to a broader framework called the NICE model, named after the city in France where it was developed. The NICE model describes a period of dramatic planetary migration that occurred in the first several 100 million years after the solar system formed. In this model, the giant planets originally orbited in a more compact configuration, closer to the Sun and closer to each other. At some point, Jupiter and Saturn crossed a mutual orbital resonance that destabilized the entire outer solar system. Uranus and Neptune were scattered outward into the planetesimal disk, plowing through it with catastrophic effect. As they migrated outward, their gravitational influence scattered planetesimals in every direction. Some were flung inward, bombarding the inner planets in an episode known as the Late Heavy Bombardment, the same event that cratered the Moon and left its face permanently scarred. Others were scattered outward on highly elongated orbits, reaching thousands or tens of thousands of astronomical units from the Sun. Many of those outward scattered objects were ejected entirely, but a significant fraction remained bound. Their orbits gradually circularized and randomized by the galactic tide and the gravitational influence of the Sun's birth cluster. These survivors became the Oort Cloud. The Sun did not form alone. It emerged from a molecular cloud along with hundreds or thousands of sibling stars in a stellar nursery, similar to the Orion Nebula or the Carina Nebula visible today. For the first few tens of millions of years, the Sun was embedded in this dense birth cluster, surrounded by neighboring stars at distances far closer than any star is to us today. The gravitational interactions within this cluster were intense. Planetary systems in formation were close enough to affect each other. Planetesimals flung outward by one star's giant planets could be captured by a neighboring star. The dense stellar environment of the birth cluster helped decouple the scattered planetesimals from the planetary region by raising their perihelia while they were at their greatest distances from the Sun, before they could swing back into the reach of the giant planets. This is one of the primary mechanisms believed to have populated the Inner Hills cloud region. Once the birth cluster dispersed, as all stellar clusters eventually do, the Sun found itself in the relative isolation it occupies today. The Oort cloud it carried with it contained a population of objects shaped by both the planetary scattering of the early solar system and the cluster environment in which that scattering occurred. The detailed structure of the Oort cloud, including the properties of objects like Sedna with its extreme detached orbit, preserves information about those early conditions that cannot be recovered from any other source. The Oort cloud is, in this sense, a fossil of the solar system's birth environment, a frozen archive of conditions that existed more than 4 billion years ago and that are otherwise completely inaccessible to direct study. Recent research has continued to refine this picture in important ways. A 2025 paper published in Astronomy and Astrophysics examined the relationship between the Oort cloud's current mass and the Sun's early history. The model suggests the Oort cloud's mass, estimated at between roughly 2/10 and 2 Earth masses, is best explained if the Sun departed its parent star cluster within about 20 million years after the giant planets formed. This constrains the Sun's birth environment and links the Oort cloud's properties to events that occurred at the very dawn of the solar system. But perhaps the most striking recent development arrived from an entirely unexpected direction. In September of 2024, curators at the Hayden Planetarium in New York City were preparing a new show called Encounters in the Milky Way. The show included a detailed visualization of the solar system's outer regions. Built from simulation data provided by David Nesvorny, a planetary scientist at the Southwest Research Institute who had spent years modeling the Oort cloud's formation and dynamics. When the team projected the scene onto the planetarium dome, astrophysicist Jackie Faherty noticed something strange in the visualization of the inner Oort cloud. A spiral, 2 distinct arms curling outward like a miniature galaxy, clearly visible in the data. At first, Nesvorny suspected an artifact, a glitch in the rendering or a distortion introduced by the visualization software. But when he went back to his raw simulation data, the spiral was there too. He had simply never looked at the data in the 3-dimensional Cartesian coordinates that the planetarium projection used. In his standard analytical framework, the structure had been invisible. Viewed from the right perspective, it was unmistakable. Nesvorny used a NASA supercomputer to run additional simulations, testing whether the spiral persisted under different parameters, different stellar encounter histories, and different initial conditions. It did. Every simulation produced the same basic structure, a two-armed spiral in the inner Oort Cloud, approximately 15,000 astronomical units across, oriented roughly perpendicular to the galactic plane. The physical explanation is elegant. Objects in the inner Oort Cloud, at distances between roughly 1,000 and 10,000 astronomical units, exist in a region where both the sun's gravity and the galactic tide are significant forces. The galactic tide, the gravitational influence exerted by the combined mass of stars and dark matter in the Milky Way, acts on these distant objects by slowly rotating their orbital planes and modifying their eccentricities. This process, governed by a phenomenon known as Kozai-Lidov oscillations, does not act uniformly on all objects. Its effects depend on each object's specific orbital parameters. The result is that objects at different distances and inclinations evolve at different rates, creating a systematic twisting pattern over billions of years. This differential evolution produces a spiral structure in physical space, with two arms winding outward from the inner edge of the cloud. The spiral is remarkably stable. Nesvorny's simulations showed that it formed early in the solar system's history, within the first few 100 million years, and has persisted to the present day. Even close stellar passages, which can temporarily disrupt the outer Oort Cloud, leave the inner spiral largely intact because the objects composing it are more tightly bound to the Sun and less susceptible to external perturbation. The discovery was published in early 2025. It represents a candidate finding, not yet independently confirmed through direct observation. Directly detecting the spiral would require identifying hundreds of individual Oort Cloud objects and mapping their three-dimensional positions, a task that remains beyond current observational capability. The Vera C. Rubin Observatory, which recently began operations in Chile, may discover dozens of individual Oort Cloud objects through its legacy survey of space and time. But Nesvorny himself has noted that dozens are not enough. Hundreds would be needed to produce a meaningful visualization of the spiral pattern. Still, the discovery is significant for what it reveals about the Oort Cloud's nature. For decades, the standard picture of the inner cloud was a relatively featureless, flattened distribution of icy bodies. The spiral findings suggest the Oort Cloud possesses internal architecture shaped not just by the Sun and the planets, but by the galaxy itself. The Milky Way's gravitational field has literally sculpted the structure of the solar system's outermost region, twisting it into a pattern that resembles, on a vastly smaller scale, the spiral arms of the galaxy that created the force responsible. The inner Oort Cloud carries the fingerprint of the Milky Way written into its shape. This discovery reinforces a deeper point about the Oort Cloud's nature. It is not a static, frozen relic. It is a dynamic structure, continuously shaped by forces operating on timescales of millions and billions of years. The galactic tide rotates orbits. Passing stars dislodge members. The giant planets scatter material outward from the inner solar system. Material flows between the inner and outer cloud regions. Comets are sent spiraling inward toward the Sun, where they briefly blaze before being consumed or ejected. The Oort Cloud is alive in a gravitational sense, responding continuously to the galaxy around it. The mechanisms that dislodge comets from their distant orbits involve forces that originate far beyond the solar system. The first is stellar perturbation. The Sun orbits the galactic center along with hundreds of billions of other stars, and over millions of years, other stars occasionally pass through the Sun's general neighborhood. Even a star passing within 1 light-year would have negligible effect on anything inside Neptune's orbit. But at the outer reaches of the Oort Cloud, where objects are only loosely bound to the Sun's gravity, the gravitational nudge from a passing star can be significant. A star passing within a light-year or two can slightly alter the orbits of outer cloud objects, changing their trajectories just enough to send some falling inward toward the Sun on new, highly elongated paths. The second mechanism, and in many ways the more fundamental one, is the galactic tide. The Milky Way galaxy contains roughly 200 to 400 billion stars, along with vast quantities of gas, dust, and dark matter, all distributed in a disk and halo structure through which the Sun orbits on a timescale of about 225 million years. The combined gravitational influence of this galactic mass creates a tidal field that acts on everything within the galaxy, including the outermost objects orbiting our Sun. For the planets and for Kuiper Belt objects, the galactic tide is negligible compared to the Sun's gravity. But as you move outward through the Oort Cloud, the Sun's gravity weakens, while the galactic tide remains roughly constant. At some critical distance, the two forces become comparable. The galactic tide can then rotate orbital planes, increase or decrease orbital eccentricities, and raise or lower perihelion distances. When the galactic tide lowers an Oort cloud object's perihelion enough that it begins to interact with the giant planets, the object enters the inner solar system as a new long-period comet. Research over the past several decades has revealed that the galactic tide and stellar perturbations work together in synergy. The galactic tide systematically evolves the orbits of Oort cloud objects over long timescales, while passing stars inject bursts of random perturbation that can accelerate the process. This synergy explains why the supply of long-period comets remains relatively steady over time, rather than arriving in dramatic pulses. The two mechanisms complement each other, maintaining a continuous trickle of comets from the outer reservoir into the inner solar system. Close stellar encounters are not rare events on astronomical timescales. On average, a star passes within roughly 3 light-years of the Sun every 100,000 years or so. Most passages are distant enough that their effects are minor, but occasionally a star passes much closer. The most dramatic upcoming encounter that astronomers have identified involves a star called Gliese 710, a small orange dwarf currently about 64 light-years away. Based on precise measurements from the Gaia spacecraft, Gliese 710 is heading almost directly toward the Sun. In approximately 1.3 million years, it will pass deep into the inner Hills cloud at a distance of roughly 10,000 astronomical units from the Sun, possibly closer. At that distance, well within the denser Hills cloud region, its gravitational influence will be significant enough to disrupt the orbits of millions or billions of Oort cloud objects. Some will be flung outward, lost to interstellar space forever. Others will have their orbits deflected inward, their perihelion distances lowered enough that they begin falling toward the inner solar system. Over the following few million years, the inner solar system will experience a shower of new comets, visitors dislodged from the outer reaches by the gravitational handshake of a passing star. Now consider the true scale of what has just been described, because knowing that the Oort cloud exists is one thing. Understanding what that existence implies for the size of your cosmic address is something else entirely. Start with something familiar. The distance from Earth to the Sun is 1 astronomical unit, roughly 93 million miles. Light covers this distance in about 8 minutes and 20 seconds. If you could drive at 60 miles per hour without stopping, the trip would take approximately 177 years. That is your baseline. 1 astronomical unit, Neptune, the outermost planet, orbits at 30 astronomical units. Light from the Sun reaches Neptune in about 4 hours and 10 minutes. At highway speed, driving to Neptune would take roughly 5,300 years. You would have departed before the construction of Stonehenge and still not arrived. The Kuiper Belt extends to roughly 50 astronomical units. The heliopause sits at about 120. These are the last landmarks most people have heard of. Now step into the Oort cloud. The inner edge of the Hills cloud is thought to begin at approximately 2,000 to 5,000 astronomical units from the Sun. Take the lower estimate of 2,000 astronomical units. That is already 67 times farther from the Sun than Neptune. In raw distance, 2,000 astronomical units equals roughly 186 billion miles. Light from the Sun takes about 11.5 days to reach this point. At highway speed, the drive would take 354,000 years. But 2,000 astronomical units is only the threshold. It is where the Oort cloud begins, not where it ends. The Hills cloud extends outward to perhaps 20,000 astronomical units. At that distance, sunlight needs about 4 months to arrive. You are now 667 times farther from the Sun than Neptune. From the outer reaches of the Hills cloud, the Sun would appear as an exceptionally bright star, visually indistinguishable from other bright stars in the sky, except for the fact that your orbit still traces a vast lazy ellipse around it over millions of years. The outer Oort cloud begins beyond the Hills cloud and extends to at least 50,000 astronomical units. At this distance, the Sun's light takes approximately 9.5 months to arrive. You are now roughly 4/5 of a light year from the Sun. The Sun still shines as the brightest star in your sky, a brilliant pinpoint, roughly as luminous as Jupiter appears from Earth. But it is nothing more than a point, no disk, no perceptible warmth reaching across that staggering vacuum. You are still orbiting the Sun, still gravitationally bound, still technically inside the solar system. But the experience of being in the solar system would be completely unrecognizable compared to anything in the familiar diagram. Now pushed to the estimated outer boundary of 100,000 astronomical units. This is the distance most commonly cited as the Oort Cloud's outer limit, though some models suggest it could extend considerably farther. At 100,000 astronomical units, you are approximately 1.5 light years from the Sun. Sunlight needs a year and a half to reach you. The Sun still shines as one of the brightest stars visible, roughly matching Sirius in apparent brilliance. But that bright point delivers no more heat or illumination to your surroundings than Sirius delivers to Earth, which is to say, effectively, nothing. The Sun is still bright. It is simply no longer a sun. It is a star, one brilliant point among many, offering light you can see but never feel. And you are still inside the solar system, 1.5 light years. Hold that number for a moment. Proxima Centauri, the nearest known star to the Sun, lies at approximately 4.25 light years. If the Oort Cloud's outer edge sits at 1.5 light years, then the Sun's domain extends more than 1/3 of the way to the nearest neighboring star. Some estimates push the outer boundary to 2 or even 3 light years, meaning the solar system might reach halfway to Proxima Centauri, possibly even farther. The space between our Sun and its closest stellar neighbor is not empty interstellar void from edge to edge. A significant fraction of that gap may still belong to our solar system, filled with trillions of icy bodies tracing vast orbits in frozen darkness. To make this scale concrete in a different way, consider time. As of 2026, Voyager 1 is approximately 165 astronomical units from the Sun. It has been traveling for nearly 49 years and has not yet reached 0.2% of the way to the Oort Cloud's outer edge. At its current speed of roughly 38,000 miles per hour, Voyager 1 will reach the inner edge of the Oort Cloud in roughly 300 years. It will not exit the outer boundary for approximately 30,000 years. 30,000 years. When Voyager 1 finally leaves the Oort Cloud, the entire span of recorded human history from the earliest cave paintings to the present day will have elapsed roughly once during the crossing. The spacecraft will have been traveling continuously for over 30 millennia and will only then have passed through the Sun's outermost sphere of gravitational influence. Communication across these distances presents its own kind of vertigo. Radio signals travel at the speed of light. If humanity ever sent a probe to the outer Oort Cloud at 100,000 astronomical units, a command transmitted from Earth would take a year and a half to arrive. The probe's confirmation signal would take another year and a half to return. 3 years of silence between a question and its answer. If something went wrong, mission controllers would not learn about the failure until 18 months after it happened. Any corrective instruction they sent would not arrive for another 18 months after that. The probe would be on its own in every practical sense, a machine operating in a darkness so remote that even light, the fastest messenger the universe allows, cannot bridge the gap in under a year. Volume scales with the cube of the radius. If the Oort Cloud's outer boundary is more than 3,000 times farther from the Sun than Neptune, then the volume of the Oort Cloud sphere is roughly 37 billion times larger than the volume of the sphere enclosing the planetary solar system. 37 billion times. The planets and moons and asteroids and Kuiper Belt objects all reside within an almost inconceivably tiny fraction of the total volume claimed by the Sun's gravitational domain. Think of it this way. If the Oort Cloud were a sphere the size of the Earth, the planetary solar system at its center would be a sphere roughly 4 kilometers across, a small hilltop village swallowed inside an entire world. All 8 planets, all their moons, the asteroid belt, the Kuiper Belt, every spacecraft humanity has ever launched, every photograph ever taken of a solar system object, all of it fits inside a volume that, relative to the Oort Cloud, is smaller than a village compared to the entire globe. If you drew the Oort Cloud as a circle the size of a classroom wall, the planetary solar system at its center would be smaller than the period at the end of this sentence. Not a small dot. The period. The full stop. That is the entire realm of human space exploration. Every mission, every flyby, every landing, every telescope image, reduced to a punctuation mark inside a sphere that extends to the walls and far beyond. Any diagram that shows the planets large enough to see necessarily truncates the solar system at Neptune. Including the Oort Cloud at the same scale would require a sheet of paper stretching from one end of a football field to the other, with the planets clustered in an invisible speck at the center. The familiar diagram is not a simplification. It is a radical amputation, showing you less than 1/1000th of the real structure and asking you to treat it as the whole. In a scale model, where the Sun is a basketball and Neptune sits half a mile away, the inner edge of the Oort Cloud would begin roughly 33 miles from the basketball. That is already outside most towns. The outer edge at 100,000 astronomical units would sit approximately 1,600 miles away. In the United States, that is the distance from New York City to Denver. In Europe, it is the distance from London to Moscow. The basketball sun sits on the sidewalk. Neptune is a small bead down the road, barely visible in the distance, and the outer boundary of the solar system is in a different time zone. Neptune orbits at 30 astronomical units. If the Oort Cloud extends to 100,000 astronomical units, then Neptune orbits at 0.03% of the solar system's total radius. 0.03%. The outermost planet sits so close to the Sun relative to the full extent of the solar system that it barely registers on any honest scale. The Kuiper Belt, stretching to 50 astronomical units, still sits within the innermost 0.05%. The heliopore's boundary, where the solar wind stops, is at roughly 120 astronomical units, roughly 0.12% of the total. Radius, everything you have ever heard described as the edge of the solar system, is within the first fraction of 1% of its actual extent. Now confront what the Oort Cloud's scale means for the concept of a boundary itself. Every map humanity has ever drawn required an edge, the coastline of a continent, the border of a nation, the property line of a yard. Maps work because they have boundaries, clean lines separating what belongs inside from what belongs outside. The human mind organizes reality by sorting things into containers with defined limits. The solar system was supposed to have an edge. For centuries, that edge was implicit in every diagram, every model, every description of our cosmic neighborhood. The planets orbit the Sun. Beyond the last planet, the solar system ends. Interstellar space begins. A clean line, a clear boundary. Inside is home. Outside is the void. The Oort Cloud destroys this boundary. It does not blur it slightly. It does not push it outward to a new, farther location where a clean line can be redrawn. It eliminates the concept of a boundary entirely. The Oort Cloud reveals that the solar system does not end. It fades, and the region across which it fades is so vast, so gradual, and so interpenetrated with the forces of the wider galaxy that no line can be drawn anywhere along its length without being arbitrary, in a way that strips the line of real meaning. At the center, the Sun's gravity is overwhelming. Moving outward, that grip weakens. Neptune, at roughly 2.8 billion miles, takes 165 years to complete a single orbit. The Sun still holds Neptune firmly, but in the Oort Cloud, the leash becomes gossamer. At 50,000 astronomical units, an icy body orbits the Sun once every 10 million years or more. Its orbital velocity is measured not in miles per second, but in fractions of a mile per second. It drifts. The Sun's gravitational pull at that distance is not zero, but it is so weak that other forces begin to compete with it on nearly equal terms. The most important of those competing forces is the galactic tide. The Milky Way contains roughly 200 to 400 billion stars, along with vast quantities of gas, dust, and dark matter, all distributed in a disk and halo structure. The combined gravitational influence of this mass creates a tidal field that acts on everything within the galaxy. For the planets and for Kuiper Belt objects, the galactic tide is negligible compared to the Sun's gravity. But as you move outward through the Oort Cloud, the Sun's gravity weakens while the galactic tide remains constant. At some critical distance, the two forces become comparable. Beyond that distance, the galaxy's gravitational influence begins to dominate. Objects can no longer maintain stable orbits. They are stripped away, claimed by the Milky Way, lost to interstellar space. This transition distance is described using the concept of the Hill sphere, the region around any orbiting body within which its gravity dominates over the tidal forces of the larger body it orbits. For the Sun orbiting the center of the Milky Way, the Hill sphere has a radius of roughly 1 to 2 light-years. This radius roughly corresponds to the outermost estimates of the Oort Cloud's boundary. That is not a coincidence. The Oort Cloud extends as far as the Sun's gravitational authority allows, and no farther. Its outer edge is defined not by any intrinsic property of the cloud itself, but by the point at which the galaxy takes over. But this transition is not a wall. It is a gradient. There is no distance at which the Sun's gravity suddenly drops to zero and the galaxy's tidal force suddenly activates. Both forces operate continuously at every distance. What changes is their ratio. Close to the Sun, solar gravity overwhelms the galactic tide by factors of billions. At the outer Oort Cloud, the two forces are in rough balance, and the Sun's hold on individual objects becomes tenuous, contingent, uncertain. Some objects at these distances are bound, others are not. The difference depends on the specifics of each object's orbit, its velocity, its direction, and the particular gravitational perturbations it has experienced from passing stars over 4.5 billion years. The outer edge of the solar system is not a boundary in any physical sense. It is a probability distribution. The fraction of objects that are gravitationally bound decreases gradually with distance, from nearly all at the inner Oort Cloud to essentially none where the galactic tide has swept everything away. There is only a vast transitional region where belonging to the solar system becomes progressively less certain, less stable, less meaningful. This boundary question is further complicated by the physical reality of matter actually crossing it. In October of 2017, astronomers detected an object moving through the inner solar system on a trajectory that was unmistakably interstellar. Its orbit was hyperbolic, meaning it was not gravitationally bound to the Sun. It had entered the solar system from outside, swung past the Sun, and was on its way back out, never to return. The object was named Oumuamua, a Hawaiian word meaning something close to scout or messenger from afar. It was the first confirmed interstellar object ever detected passing through our solar system. Oumuamua was small, estimated at a few hundred meters across, and its exact nature remains debated. It showed no visible coma or tail, leading some researchers to classify it as an asteroid rather than a comet. Others noted a slight anomalous acceleration as it departed the inner solar system, consistent with outgassing from volatile ices hidden beneath a surface crust, or, in one hypothesis that attracted significant attention, with some form of radiation pressure acting on an unusually thin, flat object. Its origin star is unknown. It could have been ejected from any planetary system in the galactic neighborhood millions or billions of years ago, drifting through interstellar space until it happened to pass through the Sun's gravitational domain, close enough to be detected. 2 years later, in August of 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor, now known as Comet Borisov. Unlike Oumuamua, Borisov was unambiguously a comet. It displayed a clear coma and tail, confirming the presence of volatile ices vaporizing as it approached the Sun. Its chemical composition was broadly similar to solar system comets, suggesting that the processes of planetary formation and planetesimal scattering that built our Oort Cloud operate similarly around other stars. Borisov was a piece of another star's cloud, ejected from its home system long ago and wandering the galaxy until chance brought it through ours. Statistical models based on the detection rates of Oumuamua and Borisov suggest that at any given moment there may be thousands of interstellar objects larger than 100 meters passing through the volume of space inside Neptune's orbit. The solar system is not sealed off from the galaxy, it is permeable. Objects from other stars' Oort clouds are constantly drifting through our territory, and objects ejected from our own Oort cloud are drifting through theirs. This means the boundary between our solar system and the rest of the galaxy is being physically crossed in both directions continuously by solid objects carrying material from foreign planetary systems. If the Oort cloud extends to 1.5 to 2 light years from the Sun, and Proxima Centauri sits at approximately 4.25 light years. Then, the gap between the Sun's outermost gravitational territory and the nearest neighboring star is only about 2 to 3 light years. If Proxima Centauri possesses its own cloud of distant icy debris, which is entirely plausible given that Oort cloud-like structures are predicted to be a common outcome of planetary formation around stars with giant planets, then the outer edges of the two clouds may approach each other across the intervening space. In this picture, the space between stars is not a vast empty desert with isolated oases of planetary systems scattered through it. Instead, each star sits at the center of an enormous gravitational domain, its territory extending outward until it meets the territory of its neighbors. The interstellar medium is partitioned into overlapping, competing, fading zones of gravitational influence with no clean gaps between them. You do not leave one solar system and then travel through empty space before arriving at another. You leave one star's fading grip and almost immediately enter the growing influence of the next. The Oort cloud is also not the same structure it was 1 billion years ago. Its population has churned, its members have been exchanged, Its boundaries have shifted in response to every stellar passage, every galactic tidal cycle, every gravitational perturbation from the wider Milky Way. The solar system is not a permanent structure. It is a process, an ongoing negotiation between the sun's gravity and the galaxy's influence, with the Oort Cloud as the contested territory where that negotiation plays out across timescales that dwarf all of human history. This impermanence applies to the future as well. The sun will continue orbiting the galactic center, passing through regions of varying stellar density, encountering molecular clouds, and experiencing tidal forces that change as its position within the galactic disk shifts over hundreds of millions of years. In dense stellar regions, close encounters will strip more objects from the outer cloud, shrinking the solar system's effective boundary. In quieter regions, the cloud will relax and spread outward. The solar system breathes, expanding and contracting over galactic timescales in rhythm with its journey around the Milky. Weight models of Oort cloud evolution suggest that the cloud may have lost a significant fraction of its original population over the solar system's lifetime. The domain our sun claimed when the Oort cloud was young and freshly populated was larger than the domain it claims today. The erosion continues. 2 billion years from now, the Oort cloud will be thinner, sparser, and its effective outer edge will have crept closer to the sun. The solar system is not only boundaryless in space, it is shrinking in time. The home we cannot fully map is also a home we are slowly losing. The Oort cloud is not empty in the way that a vacuum chamber is empty. It is emptier. It is emptier than the space between planets. It approaches the emptiness of the most desolate regions in the observable universe. And yet it contains trillions of solid objects. They simply occupy so little of the available volume that they might as well not be there at all from a density perspective. Consider the population density. If the outer Oort cloud contains roughly 1 trillion objects spread throughout a spherical shell between 20,000 and 100,000 astronomical units, the average distance between any two neighboring objects is on the order of billions of miles, roughly 10 to 30 times the distance from the Earth to the Sun. That is not a crowded environment. That is a void punctuated by the occasional frozen mountain, separated from its nearest neighbor by a gulf comparable to the distance from the Sun to Saturn or beyond. An observer sitting on one Oort cloud body and looking in every direction would see nothing. No nearby companions, no glinting surfaces catching faint sunlight, no sense of belonging to a population at all, just stars and darkness, indistinguishable from any other patch of deep space. If you flew through the Oort cloud in a spacecraft, you would have no sensory evidence of its existence, no thickening of surrounding material, no increased frequency of particle impacts on your hull, no change in the star field outside your window. You could cross the entire Oort cloud from inner edge to outer boundary and never once encounter a detectable object, never once register a gravitational anomaly, never once have any reason to believe you were inside a structure at all. The Oort cloud is there, confirmed by every line of evidence that comet science can bring to bear, and it is simultaneously, in terms of direct sensory experience, nothing. A ghost written in gravity and statistics, rather than in matter dense enough to see or touch. The mass figures reinforce this strangeness. The Oort cloud, despite containing perhaps 1 trillion or more individual objects, has a total mass that is startlingly small. Current estimates range from as little as a fraction of an Earth mass to as much as several Earth masses depending on the model. That is the combined mass of every single object in the cloud. Every frozen mountain, every icy boulder, every primordial snowball drifting through that enormous sphere. All of it together may weigh less than a handful of Earths. Jupiter alone has a mass of roughly 318 Earths. Saturn weighs about 95. Even Uranus, the least massive of the giant planets, weighs roughly 14.5 Earths. The entire Oort cloud, stretching from thousands of astronomical units out to 100,000 or beyond, spanning light years of space, containing trillions of individual bodies, is less massive than Uranus. The most voluminous structure in the solar system is also one of the least massive. The average density of the Oort cloud is so low that expressing it in human terms requires either scientific notation or a long string of decimal places before reaching the first non-zero digit. This archival quality of Oort cloud objects extends to their composition, which represents one of the most scientifically significant aspects of what the cloud actually is. Because these bodies were formed from the protoplanetary disk and then quickly placed into cold, distant orbits where chemical processing is essentially non-existent, They represent some of the least altered material in the solar system. Every comet that reaches us from the outer Oort Cloud carries a chemical signature that has been essentially unchanged since the solar system formed. The water ice in a long-period comets. Nucleus last experienced liquid conditions, if ever, in the protoplanetary disk more than 4 billion years ago. The complex organic molecules in its surface layers were synthesized in the interstellar medium before the solar system formed and survived the accretion process intact. Studying the composition of long-period comets is therefore one of the best windows astronomers have into the chemical conditions of the early solar system. This compositional connection has motivated intensive observational campaigns over the past several decades. Spectroscopic studies of cometary comae and tails have revealed that comets contain water in abundance along with carbon monoxide, carbon dioxide, methane, ethane, hydrogen cyanide, methanol, and dozens of other organic and inorganic compounds. The relative abundances of these compounds vary from comet to comet, reflecting differences in the conditions at the specific location in the protoplanetary disk where each comet originally formed. Objects that formed in the colder outer reaches of the disk tend to be richer in the most volatile ices. Objects that formed in warmer inner regions carry a slightly different chemical fingerprint. By comparing the compositions of many comets, astronomers can reconstruct a chemical map of the protoplanetary disk piece by piece, each comet providing a sample from a different location in a disk that no longer exists as a coherent structure. The water in comets has attracted particular attention because of its relationship to the water on Earth. Our planet's oceans contain an enormous amount of water, far more than could have been retained from the material that originally formed the Earth in the hot inner solar system. Much of Earth's water was delivered after the planet formed by impacting bodies from the outer solar system. The isotopic composition of Earth's water, specifically the ratio of deuterium to ordinary hydrogen, provides a clue to its origin. Different populations of outer solar system objects have characteristic deuterium to hydrogen ratios. Studies of multiple comets have shown that Kuiper Belt comets, those with short orbital periods, tend to have ratios that more closely match Earth's oceans than the ratios measured in long-period comets from the Oort Cloud, suggesting that Kuiper Belt objects may have been the primary source of Earth's water. But the picture is not simple. Some long-period comets show ratios closer to Earth's value, and the sample of measured comets is still relatively small. The question of where Earth's water came from remains an active area of research, and the answer depends critically on understanding the full population and composition of both the Kuiper Belt and the Oort Cloud. Beyond water, comets carry complex organic molecules that have been identified as precursors to the building blocks of life. The amino acid glycine has been detected in samples returned from short-period comets. Larger and more complex organic molecules have been identified spectroscopically in the comae of long-period comets. The presence of these molecules in Oort Cloud material suggests that the chemical raw materials necessary for life were already present in the outer solar system before Earth formed, and that comet impacts may have contributed organic chemistry to the early Earth's surface. This connection between the Oort Cloud and the origin of life is speculative, but not dismissible. It represents one of the more profound implications of the cloud's existence, that the vast frozen reservoir at the edge of our solar system may be chemically linked to the conditions that allowed biology to emerge on at least one planet in the system's warm inner core. The question of whether the Oort Cloud is unique to our solar system or whether all planetary systems possess similar structures is one of the central open questions in planetary science. Current theory strongly suggests that Oort Cloud-like structures should be common. Any planetary system with giant planets will produce large numbers of scattered planetesimals. If the system formed in a stellar cluster interactions would help decouple those planetesimals and trap them in stable distant orbits. Detecting Oort clouds around other stars is extraordinarily difficult. The individual objects are far too small and dark to resolve with any current or planned telescope at interstellar distances. But there are indirect ways to probe the outer regions of other planetary systems. Studies of white dwarf stars, which often show traces of rocky and icy material accreted from their surrounding planetary systems, can reveal information about outer cometary reservoirs that feed material toward the dying star as its luminosity and gravitational influence change during the death process. Some white dwarfs show evidence of accreting water-rich material similar in composition to outer solar system comets, suggesting that Oort Cloud-like Reservoirs around other stars are indeed sending material inward as their host stars evolve. The interstellar visitors Oumuamua and Borisov provide perhaps the most direct evidence that Oort Cloud-like structures exist around other stars. These objects were ejected from their home systems, presumably through the same kind of planetary scattering processes that populated our own Oort Cloud, and drifted through interstellar space until gravitational focusing by the Sun brought them close enough to detect. The rate at which such visitors are arriving implies that stellar systems in the solar neighborhood eject enormous numbers of planetesimals over their lifetimes, consistent with the expectation that Oort Cloud populations are continuously leaking objects into the interstellar medium. The detection of these visitors also opened a new window on interstellar material exchange. If stellar systems eject planetesimals into the interstellar medium, and if the density of such objects is high enough for occasional captures to occur, then material from other planetary systems can be incorporated into our own Oort Cloud over the solar system's lifetime. Computer simulations of this process suggest that the Oort Cloud may indeed contain a small but non-negligible fraction of objects that originated around other stars. These captured interstellar visitors would be physically indistinguishable from the rest of the cloud's population without detailed spectroscopic study of their composition. But if they are eventually dislodged and sent inward as comets, their compositions might differ from those of native solar system objects, providing another avenue for studying the chemical diversity of planetary systems across the galaxy. There is a final dimension to the Oort Cloud story that rarely gets the attention it deserves, and it concerns deep time in a different sense than formation history. The Oort Cloud connects the present moment to the deep past through the comets it delivers. Every long-period comet that reaches our skies is a sample of primordial material that spent billions of years in frozen storage at the edge of the solar system before being dislodged and sent inward on its current journey. The comet's nucleus, a dark lump of ice and dust a few miles across, is essentially a time capsule. Its surface layers may have been processed by cosmic rays and sparse interstellar ultraviolet radiation during billions of years of storage, building up a darker radiation crust. But beneath that crust, the interior ice preserves the original chemical composition of the protoplanetary disk essentially intact. When a long-period comet approaches the Sun for the first time in billions of years, solar heating vaporizes the ice from the nuclear surface, releasing the preserved volatile compounds into space in the coma and tail. In a very real sense, a first-time long-period comet is releasing material into the solar system that was last in a chemically active environment more than 4 billion years ago. Observing that material through spectroscopy allows astronomers to read chemical information encoded in the protoplanetary disk when Earth was not yet formed and the solar system was a swirling disk of gas and dust around a young star. The Oort Cloud is, therefore, not just a gravitational structure. It is a library, a vast, cold, dark archive of primordial material, maintained at temperatures barely above absolute zero for billions of years, accessible only through the occasional volume that finds its way inward and briefly becomes visible as a comet in our skies. Most of the library will never be accessed. The overwhelming majority of Oort Cloud objects will orbit in frozen silence for the remaining lifetime of the Sun, their contents never read by any observer, their existence registered only as a statistical signal in the orbital mechanics of the comets that do arrive. The library exists, it is enormous, and we have access to only a tiny fraction of its holdings. This is the true nature of the Oort Cloud, and it is a nature that defies simple description. It is simultaneously a gravitational structure of staggering scale, a dynamical system continuously shaped by galactic forces, a chemical archive of the solar system's formation, a permeable boundary between our stellar system and the interstellar medium, and a reservoir that has been sustaining the comet supply for 4.5 billion years with no sign of exhaustion. It is also, by any measure, the largest and least understood component of the solar system we call home. Everything humanity knows about space, every discovery made by every telescope ever pointed at the sky, every sample returned by every mission ever launched, came from within the innermost fraction of 1% of the Sun's total gravitational domain. The remaining 99.9%, the dark sphere of trillions of frozen objects stretching from thousands to hundreds of thousands of astronomical units in every direction, remains entirely beyond the reach of direct observation. It is known only through the comets it sends and the physics that explains them. What comes next in understanding The Oort Cloud depends on technology that does not yet fully exist and on surveys that are just beginning to operate. The Virasi-Rubin Observatory represents the best near-term hope for direct detection of individual Oort Cloud objects in the transitional Sedna-like region. Its legacy survey of space and time, expected to run for a decade, will scan the southern sky repeatedly with unprecedented depth and cadence, potentially discovering dozens of objects in the inner cloud region that are temporarily close enough to reflect measurable amounts of sunlight. Future space telescopes with larger apertures and improved sensitivity to faint, slow-moving objects may extend this capability further. The Nancy Grace Roman Space Telescope may contribute to this search through its wide-field imaging capabilities. Beyond individual object detection, astronomers are also exploring whether gravitational microlensing, the temporary brightening of background stars caused by intervening massive objects, could be used to probe the Oort Cloud population statistically. While challenging given the small masses of individual Oort Cloud objects, statistical analyses of microlensing events might eventually provide independent constraints on the cloud's total mass and population distribution. The Gaia mission, which has produced the most precise three-dimensional map of nearby stellar positions and motions ever assembled, is enabling better predictions of future stellar encounters with the Sun. By identifying which stars will pass close to the solar system over the next few million years, Gaia allows astronomers to predict future comet showers with greater accuracy and to study how the outer Oort Cloud responds to individual stellar passages over time. What scientists still do not know about the Oort Cloud is in many respects more interesting than what they do know. The total population and mass of the cloud remain uncertain by factors of several, largely because the only direct evidence comes from the comets that reach us, which represent a tiny and potentially unrepresentative sample of the broader population. The exact outer boundary is unknown. Whether the cloud truly extends to 100,000 astronomical units or to 200,000 or somewhere in between depends on models and assumptions that have not yet been tested by direct observation. The question of how much of the cloud's mass consists of material that originally formed around the Sun versus material captured from other stars during the Sun's birth cluster phase remains open. If a significant fraction of Oort Cloud objects formed elsewhere, that has profound implications for understanding the chemical inventory of the cloud and the ways in which planetary systems exchange material across the galaxy. The spiral structure recently identified in simulations of the inner Oort Cloud awaits observational confirmation. If the Rubin Observatory or future surveys discover hundreds of Oort Cloud objects with measurable three-dimensional positions, testing whether those positions match the predicted spiral pattern will become one of the key observational goals in outer solar system astronomy. Over the next several decades, there is also the unresolved question of Planet 9, a hypothetical massive body that some astronomers have proposed to explain the unusual clustering of orbits among a subset of extreme trans-Neptunian objects, including Sedna and several others discovered more recently. If Planet 9 exists at a distance of perhaps 400 to 800 astronomical units from the Sun, its gravitational influence would significantly affect the inner Oort Cloud, altering the rates and directions from which comets are dislodged and sent inward. The existence or non-existence of Planet 9 therefore has direct implications for Oort Cloud dynamics. Ongoing sky surveys are searching for this object, and the Rubin Observatory's deep imaging may finally resolve the question, one way or the other, within the next decade. Somewhere out there right now, a frozen body the size of a mountain is drifting in absolute darkness at a distance of 70,000 astronomical units from the Sun. It has been orbiting for 4 billion years. It has never been warmed. It has never been photographed. It has never been touched by any instrument or signal from Earth. It belongs to the solar system, held by the Sun's gravity in an orbit that takes roughly 18 million years to complete. From its surface, the Sun is still the single brightest star in the sky, outshining even Sirius. Yet it is nothing more than a sharp point of light that provides no heat, casts no shadow, and illuminates nothing. The constellations from that vantage point are almost identical to the ones seen from Earth, because the body is still too close to the Sun relative to the distance of other stars for the stellar patterns to shift appreciably. That object is inside your solar system. It is part of your cosmic home, and it orbits in a place so remote, so cold, so dark, and so silent that it already inhabits the emptiness between stars in every way that matters to human experience. The only thing connecting it to your world is an invisible thread of gravity extending across trillions of miles of vacuum, a thread so thin that the next passing star might sever it entirely, sending the object drifting into the interstellar medium to wander the galaxy alone for eternity. The journey to another solar system does not begin at the edge of the planetary region. It does not begin at the heliopause. It begins at the far side of the Oort Cloud, a boundary so distant that reaching it represents a challenge of the same order of magnitude as reaching the nearest star itself. The first great barrier to interstellar travel is not the distance between stars. It is the distance across our own backyard. The Oort Cloud's existence is not in serious scientific doubt. Its approximate scale is known within a factor of a few. Its formation mechanism is understood in general terms. Its connection to the galactic environment is well established. What remains is the detail, the precise population, the exact boundary, the internal structure, the compositional diversity, the degree of contamination by interstellar captures, and the specific history of stellar encounters that has shaped the current distribution of its members. These are answerable questions. Given sufficient observational capability and sufficient time, they are answerable within the next few decades if current and planned facilities perform as expected. The answers will not change the fundamental conclusion that the Oort Cloud is vast beyond easy comprehension, ancient beyond direct experience, and structurally dominant in any honest account of the solar system's true extent. But they will fill in the details of a picture that is currently painted in broad, confident strokes. And they will reveal, as detailed observations almost always do, surprises and complexities that no prior model fully anticipated. The universe has a habit of being more interesting in its specifics than in its general outlines. The Oort Cloud, when its details finally become accessible to observation, will almost certainly be no exception. What is perhaps most arresting about the Oort Cloud is not any single fact about its size or composition or dynamics, but the totality of what it implies about the nature of scientific knowledge at the frontier of inquiry. Here is a structure that the scientific community considers effectively established, that planetary scientists treat as a known component of the solar system when building models and interpreting observations, that is cited in textbooks and referenced in research papers as a baseline assumption rather than a hypothesis requiring justification. And yet it has never been directly photographed. No image of an Oort Cloud object exists. No mission has ever visited the region where the Hills Cloud begins. No telescope has ever resolved the structure against the background of stars. The Oort Cloud is, in the strictest empirical sense, unseen. We know it through what it does, not through what it is. This is not an unusual situation in science. Many of the most significant structures and phenomena in the universe are known through their effects rather than through direct observation. Dark matter was established as a component of galaxies and galaxy clusters through its gravitational effects on visible matter decades before any direct detection candidate emerged. Gravitational waves were theorized from general relativity and inferred from the orbital decay of binary pulsars before the first direct detection in 2015. Black holes were mathematical solutions to Einstein's field equations for decades before observational. Evidence accumulated to the point where their existence was beyond reasonable scientific doubt. The universe routinely contains things that are real and consequential, but that require indirect inference, rather than direct observation to establish. The Oort Cloud joins this list of structures known through inference, and its inference is particularly elegant because it follows so directly from simple orbital mechanics and basic gravitational physics. Comets arrive from all directions. Their orbital aphelia cluster at tens of thousands of astronomical units. The galactic tide and stellar perturbations are sufficient to explain how objects at those distances are dislodged and sent inward. The formation models predict that a structure of the appropriate population and mass should exist at exactly those distances. The pieces fit together with a coherence that is itself a form of observational confirmation, even in the absence of a direct image. Science at its best is exactly this: the construction of a consistent, predictive, mutually reinforcing picture of how things are, built from whatever evidence the universe makes available. Sometimes that evidence is direct and visual. Sometimes it is inferential and statistical. The Oort Cloud is a monument to the inferential kind of science, to the willingness to follow the mathematics wherever it leads, even when it leads to structures so vast and so remote that direct confirmation may not be possible within any human lifetime. It is a demonstration that the universe is knowable even in its most extreme and inaccessible corners, provided we are willing to use every tool available and follow the evidence with rigor and honesty wherever it points. If you found yourself genuinely unsettled by the scale of what we just walked through, that is the appropriate response. Share this with someone whose mental picture of the solar system could use recalibrating. And if you want to keep following questions like these wherever the science actually leads, staying subscribed is the easiest way to make sure you do not miss what comes next. The Oort Cloud asks you to hold a number in your mind and sit with it without reducing it to something comfortable. 100,000 astronomical units, 1.5 light years, 30,000 years for Voyager to cross it, 1 trillion frozen objects in near total darkness, each separated from its nearest neighbor by billions of miles of vacuum, each carrying chemical memories of a solar system that existed before Earth formed, a structure so vast that the entire familiar solar system, the one with all the planets and moons and asteroids and spacecraft and photographs, fits inside it like a grain of sand at the center of a sports stadium. That is your solar system. That is your cosmic home. Most of it is dark, cold, and silent beyond any human experience of those words. Most of it has never been lit, never been touched, never been seen by any eye or any instrument built by the civilization that formed in the warm, bright, incomprehensibly tiny core at its center. Every diagram that ends at Neptune has been telling you half a story. The other half is the Oort Cloud. Vast, dark, ancient, inferred, extraordinary, and yours. The solar system is not what the diagram says it is, and knowing what it actually is changes something fundamental about how you perceive the system you have lived inside your entire life without ever truly seeing it. The place you call home already reaches into the abyss. It always has. You just never looked far enough to see it. There is a particular strangeness to how the Oort Cloud entered scientific thinking. Most major astronomical structures were discovered through direct observation first and explained theoretically afterward. Uranus was spotted through a telescope before anyone had a theoretical reason to expect it. Neptune was predicted mathematically before it was seen, but it was seen. The cosmic microwave background radiation was detected accidentally by 2 engineers trying to eliminate noise from a communications antenna before anyone fully understood what they had found. The Oort Cloud is different. It was theorized into existence through the orbital statistics of comets, not discovered through any instrument pointed in its direction. Jan Oort built the case for it from a dataset of 19 orbital solutions, a small sample by modern standards, and from the logic of what those orbits implied about a reservoir that could not be seen. The cloud was named before a single one of its members had been identified. That is a remarkable way for a structure containing perhaps 1 trillion objects to enter scientific knowledge. This means that Oort Cloud has a peculiar epistemological status that is worth thinking about carefully. It is not hypothetical in the way that early proposals for atoms were hypothetical, as entities invoked to explain observed properties without direct evidence for their physical existence. The Oort Cloud's existence is demanded by observations of comets that can be directly tracked and measured. Its broad properties are constrained by decades of orbital calculations. Its formation is explained by models that also successfully account for the broader architecture of the planetary solar system. In terms of the strength of the indirect evidence supporting it, the Oort Cloud is not much more speculative than dark matter, and dark matter is considered as well established as almost anything in modern cosmology. What the Oort Cloud lacks is not evidence. What it lacks is a photograph. And in an era where public science communication often equates seeing with knowing, that absence creates a persistent gap between how confidently scientists speak about the Oort Cloud and how tentatively it is sometimes characterized in educational materials. The gap matters because the Oort Cloud is not a minor footnote to the solar system story. It is, by volume, by radius, and by the sheer count of its members, the dominant structural component of our local cosmic neighborhood. Any honest account of what the solar system is, as opposed to what it contains in its warm, bright inner core, has to grapple with the Oort Cloud. Consider a parallel from Earth science. If someone described the Earth to you and mentioned only the continents, the oceans, and the atmosphere, they would have described a great deal of what we interact with directly, but they would have left out the interior of the planet, the mantle, and the core, which together account for more than 99% of the Earth's volume. The interior is not directly accessible. No drill has ever reached even the lower crust. We know its structure through seismic waves, through the analysis of how earthquake signals propagate through the Earth's body, and reflect from interior boundaries. We know it through indirect inference, but we do not say the Earth's interior is speculative. We treat it as established because the evidence is sufficient to establish it. The Oort Cloud stands in a roughly analogous position relative to the solar system. It accounts for far more than 99% of the Sun's gravitational domain. It is not directly accessible. We know its structure through the orbital mechanics of comets and through models of planetary formation and galactic dynamics. And the evidence is sufficient to treat it as established, not as a guess or a theoretical possibility, but as a real structure whose existence is required by the physics we observe. One aspect of the Oort Cloud that rarely gets discussed is its relationship to the question of cosmic isolation. We have a tendency, in thinking about interstellar distances, to imagine the solar system as a small island in an ocean too vast to traverse. The planets form a compact system. Around them lies a relatively empty space extending for light years to the nearest neighbors. The isolation feels total and absolute. The Oort Cloud complicates this picture in an interesting way. Our solar system is not, in any strict sense, isolated from its galactic environment. It is continuously influenced by that environment. The galactic tide shapes the orbits of Oort Cloud objects. Passing stars dislodge members and send them inward. Some of those passing stars may have originated from the same birth cluster as the Sun. Ancient siblings separated over billions of years of independent galactic orbits. The Sun's gravitational domain reaches out so far that it overlaps, or at minimum closely approaches, the domains of neighboring stars. This means that material exchange between stellar systems is not some exotic hypothetical process. It is something that has been happening continuously throughout the solar system's history. Oumuamua and Borisov are the first two interstellar visitors we have ever identified, but statistical reasoning strongly suggests they are among many. The galaxy, seen through the lens of the Oort Cloud, is not a collection of isolated systems separated by emptiness. It is a network of overlapping gravitational territories, each one continuously exchanging material with its neighbors on timescales of millions to billions of years. This perspective has implications for some of the most fundamental questions in planetary science and astrobiology. If material from other planetary systems is constantly passing through our solar system, and if some fraction of that material is captured into the Oort Cloud, then the Oort Cloud may contain objects that formed under entirely different conditions than those that produced native solar system comets. Objects from stars with different compositions, from planetary systems with different architectures, from formation environments richer or poorer in certain elements than the solar nebula. Detecting and chemically characterizing such objects, if they eventually make their way inward as comets, could provide a window into the diversity of planetary formation processes across the galaxy. The reverse is also true. Objects ejected from our Oort Cloud over the solar system's lifetime are presumably drifting through the galaxy, eventually passing through other stellar systems, potentially being captured into other Oort Clouds, and eventually becoming comets in other skies around other stars. In a very real sense, the solar system has been exporting frozen samples of its chemistry to the rest of the galaxy for 4.5 billion years. This exchange process, slow and diffuse as it is, means that the boundary between our solar system and the rest of the galaxy is not sharp, not fixed, and not one-directional. Matter flows across it in both directions on timescales long enough to require geological or even cosmological thinking to appreciate. The concept of the solar system as a bounded, self-contained system is revealed by the Oort Cloud to be an approximation, useful for many purposes, but ultimately a simplification of something far more porous and dynamic. The sheer antiquity of the Oort Cloud is worth dwelling on separately from its scale. When we say the Oort Cloud formed roughly 4.5 billion years ago, we are talking about objects that have been drifting through the same general orbits, in the same frozen darkness, since before the Earth existed, since before the Moon formed in the aftermath of a planetary collision, since before the first rocks solidified on any of the terrestrial planets, since before complex chemistry had even begun in the oceans of a proto-Earth that did not yet exist. An Oort Cloud object at 70,000 astronomical units is not just remote in space, it is remote in time, in the sense that the material composing it last experienced any kind of energetic processing before the solar system reached the form we know. The deuterium in its water ice was forged in the Big Bang. The oxygen was synthesized in stars that died before the sun was born. The carbon and nitrogen and sulfur were assembled into organic molecules in the cold, interstellar medium, and then incorporated into the solar nebula that collapsed, to form the Sun and its family of worlds. The Oort Cloud is, among other things, a repository of cosmic chemistry dating to the solar system's earliest moments. It is older than the continents, older than the ocean basins, older than life, the frozen mountains drifting through. It carry in their ice a record of conditions that preceded everything we think of as Earth history, by a margin almost too large to hold in mind. This temporal depth is part of what makes the Oort Cloud scientifically important beyond its role as a comet source. Every long-period comet that reaches us is not just an interesting visitor. It is a messenger from the deep past, carrying chemical information that has been preserved with extraordinary fidelity by the cold and dark of the outer solar system. When astronomers analyze the spectral signatures of cometary volatiles as they vaporize under solar heating, they are essentially reading a letter written in chemistry at the dawn of the solar system, preserved intact for 4.5 billion years and only now being opened. The number of such letters that have been read is small relative to the number that exist. We have studied a few dozen long-period comets in enough detail to extract meaningful chemical information. The Oort Cloud presumably contains hundreds of billions or trillions more, each with its own chemical story reflecting the particular location in the protoplanetary disk where it formed. Most will never reach us. Most will orbit in frozen silence until the Sun's expanding outer envelope sweeps them away in about 5 billion years. But the ones that do arrive carry an extraordinary payload of ancient information that our instruments are only beginning to be sophisticated enough to fully decipher. There is also a set of deeper, physical questions that the Oort Cloud forces us to grapple with, questions about what it means for something to belong to a particular physical system. In everyday life, belonging is clear. An object is either inside a container or outside it. A person is either in one country or in another. Boundaries define membership. Gravity does not work this way. The Sun's gravitational influence does not stop at any particular distance. It declines with the square of distance, growing weaker with every increase in separation, but never reaching exactly zero. At some very large distance, the Sun's pull on an object becomes so weak relative to other forces acting on it. The galactic tide, the gravitational influence of passing stars, the collective pull of other masses in the galactic neighborhood, that the Sun's claim on the object becomes merely probabilistic rather than definitive. The object may remain in orbit for the foreseeable future, or a chance perturbation may release it. It belongs to the solar system the way a tourist with a flexible schedule belongs to a city, present for now, likely to stay, but not committed to permanence. This probabilistic boundary, this zone where belonging becomes a matter of statistics rather than hard physics, is not something our everyday intuitions handle well. We are adapted to living in a world of hard surfaces and sharp edges. The gradual dissolution of gravitational membership over light years of distance is not the kind of thing natural selection prepared us to reason about intuitively. That is exactly why the Oort Cloud is such a powerful scientific and conceptual object. It forces a confrontation with the limits of everyday thinking about boundaries and belonging. The tools of scale comparison that science communicators reach for when explaining the Oort Cloud are all imperfect, but they are not useless. Each one captures something true about a different dimension of the reality. The classroom wall with the period at the center captures the visual inadequacy of the standard diagram. The basketball sun in London with the outer boundary in Moscow captures the raw physical scale of distances. The Voyager transit time of 30,000 years captures the temporal dimension of that scale. The comparison of the Oort Cloud's total mass to that of a single ice giant planet captures the paradox of vast volume and modest mass. The image of neighboring objects separated by billions of miles despite being part of the same structure captures the almost incomprehensible emptiness. None of these comparisons alone is sufficient. Together, they build towards something that the human mind can hold imperfectly but genuinely. This is the work of science communication at its most challenging and most important. Not simplifying until accuracy is lost, but finding the right scaffold of comparisons that allows a mind shaped by evolution for human-scale environments to genuinely apprehend facts that are true at inhuman scales. The Oort Cloud demands that effort. It is worth the effort not because the cloud is spectacular in the way that a nebula or a galaxy collision is spectacular, but because understanding it changes something fundamental about how you perceive the system you live in. You are not in a compact neighborhood of planets orbiting a central star. You are at the center of a sphere of frozen darkness, extending more than a light year in every direction. That sphere is your home. Most of it you will never know. But knowing it exists, knowing its size and its nature and its history and its role in the solar system story, is a different kind of knowledge from knowing the distance to Jupiter or the mass of Saturn. It is knowledge that shifts the frame. It changes the background against which every other astronomical fact takes its meaning. The solar system is not what the diagram says it is. The Oort Cloud is the proof. And the fact that the proof is written in the orbital mechanics of comets, in the simulated spiral arms of a structure no telescope has ever seen, in the gravitational records of 4.5 billion years of planetary formation and galactic sculpting, makes it no less real and no less worth understanding. It makes it more. The ongoing science of the Oort Cloud will unfold over the coming decades through instruments that are just beginning their work and missions that have not yet been approved or built. Each new discovery of an object in the transitional Sedna-like zone between the scattered disk and the inner cloud adds a data point to a picture that is still incomplete. Each new interstellar visitor detected by improving survey systems extends our statistical understanding of how common Oort Cloud-like structures are around other stars. Each improvement in our ability to model galactic tidal dynamics and stellar encounter histories sharpens the predicted structure of the cloud and the expected rate of comet delivery to the inner solar system. The science is not finished. It is not even close to finished. But the broad outlines are in place, confirmed by decades of converging evidence from orbital mechanics, numerical simulations, compositional spectroscopy, and the detection of interstellar visitors. The Oort Cloud is real. It is enormous. It is ancient. It is structurally shaped by the galaxy in ways we are only beginning to understand. And it is, in the most literal physical sense, the solar system's true outer boundary, the place where the sun's gravitational authority fades to nothing and the open galaxy begins. That is the Oort Cloud. Vast, dark, ancient, inferred, extraordinary, and yours. Every diagram that ends at Neptune has been telling you half a story. Now you know the rest. There is one more angle on the Oort Cloud that deserves attention, and it involves the relationship between what we can observe and what we are permitted to claim as knowledge. The history of science is full of cases where a theoretical prediction preceded observation by years or decades. The existence of Neptune was predicted from perturbations in Uranus's orbit before the planet was directly observed. The existence of gravitational waves was predicted by Einstein's general theory of relativity in 1916. But the first direct detection did not come until 2015, nearly a century later. In each of these cases, the prediction was eventually confirmed by direct measurement. The Oort Cloud occupies a different position. It was predicted, as we have seen, by Jan Oort in 1950, based on the orbital statistics of comets. Unlike Neptune or gravitational waves, however, there is no expectation that the Oort Cloud will be directly confirmed within any foreseeable time frame. The individual objects are too small, too dark, and too distant to resolve with any instrument that can be reasonably imagined given current or near-future technology. The structure as a whole is too diffuse and too large to image in any conventional sense. Direct confirmation, in the way Neptune was eventually confirmed, or gravitational waves were eventually confirmed, may never come. This places the Oort Cloud in a unique category within well-established astronomy. It is a structure whose existence is considered effectively certain by the scientific community, but whose direct confirmation is essentially impossible with any instrument currently imaginable. The certainty rests entirely on indirect evidence. The beauty of the case for the Oort Cloud is precisely that the indirect evidence is so strong and so self-consistent that the need for direct confirmation does not feel urgent. Consider the chain of reasoning. Long-period comets arrive from all directions at orbital periods, implying aphelia at tens of thousands of astronomical units. This is directly measured. The galactic tide and stellar perturbations have sufficient strength at those distances to dislodge objects from stable orbits and send them inward as new comets. This is calculated from well-understood physics. Planetary formation models predict that a reservoir of icy bodies at those distances should exist, populated by planetesimals scattered outward by the giant planets during the solar system's youth. This is derived from numerical simulations that also successfully explain numerous other observed features of the solar system. Recent supercomputer simulations further reveal internal structure in the Oort Cloud that is consistent with the known dynamics of galactic tidal forces acting on distant populations over billions of years. Each link in this chain rests on well-established physics. None of them requires any appeal to unknown forces or unprecedented phenomena. The Oort Cloud is, in a sense, the inevitable consequence of applying known physics to known initial conditions over known timescales. It has to exist in something like the form described if the solar system formed in the way we understand it to have formed and exists in the galactic environment we observe it to inhabit. That is a fundamentally different kind of certainty from the certainty we attach to things we have directly seen, but it is still certainty. The same kind of certainty that makes us confident that the Earth has an iron core we have never drilled to, or that stars have nuclear interiors we have never directly observed, or that the universe was once hotter and denser than it is today, even though no human was present to measure it. Physics-based inference, applied carefully and consistently, is one of the most powerful tools science possesses. The Oort Cloud is a monument to that tool. The coming decades will refine our picture of the Oort Cloud in ways we cannot fully anticipate. The Rubin Observatory will find new objects in the transitional zone and perhaps some that are clearly members of the Inner Hills Cloud. The Roman Space Telescope will add its own contribution to the census of outer solar system bodies. Future missions to comets will analyze their chemistry in unprecedented detail, adding more pages to the chemical library that the Oort Cloud has been preserving for 4.5 billion years. Better models of galactic dynamics will sharpen predictions about the cloud's structure and evolution. Improved stellar catalogues from Gaia and its successors will produce better predictions of future stellar encounters and the comet showers they will eventually produce. Each of these advances will be incremental. None will produce a direct image of the Oort Cloud as a structure, but together they will build, piece by piece, a more complete and more precise understanding of a structure that already stands as one of the most extraordinary things we know about our place in the universe. It is perhaps fitting that the solar system's largest and oldest component is also its most elusive. Everything about the Oort Cloud resists easy summary. Its scale defeats analogy. Its age defeats imagination. Its emptiness defeats the senses. Its conformation defeats conventional observation. To truly understand the Oort Cloud is to confront the limits of human intuition and to discover, on the other side of those limits, a structure more vast and more ancient and more strange than the comfortable solar system of classroom diagrams. That confrontation is not comfortable, but it is honest. And honesty about the scale and nature of the system we inhabit, uncomfortable as it sometimes is the foundation on which all real understanding is built. The solar system does not end at Neptune. It does not end at the heliopause. It ends gradually and uncertainly and provisionally, somewhere more than a light year away, at the point where the galaxy finally outcompetes the sun for gravitational sovereignty over the frozen remnants of a protoplanetary disk that no longer exists. That is your home. That has always been your home. You simply did not know how large it was. Now you do. The scale of the Oort Cloud creates a certain vertigo when applied to the human experience of living on Earth, and that vertigo is worth pursuing rather than deflecting. Every morning, the sun rises and provides enough warmth to sustain an entire biosphere. Every evening, it sets and the sky fills with stars. This daily rhythm has been the backdrop of human existence for as long as our species has existed. We have built calendars around it, religions around it, entire civilizations organized by the cycle of light and dark, driven by Earth's relationship with the nearest star. That relationship, that extraordinary intimacy with a fusion reactor burning at one astronomical unit of distance, is what we instinctively mean when we think about the sun's presence in our lives. And yet the sun's gravitational domain extends 100,000 astronomical units in every direction. The sun claims territory that it never warms, never illuminates in any meaningful way, that it barely touches even gravitationally. 1 trillion frozen objects drift in that domain, each one orbiting a star they experience as nothing more than the brightest point of light in a sky full of bright points of light. The warmth you feel in sunlight, the light that makes life possible on Earth, is almost entirely confined to the innermost fraction of 1% of the territory the sun controls. This asymmetry between the sun's influence on Earth and its influence on the Oort Cloud is one of the most striking facts about our solar system when considered clearly. The same gravitational force that holds the Earth in an orbit, perfectly calibrated for liquid water and complex life, also holds, at incomparably greater distances and with incomparably less consequence, trillions of frozen mountains in orbits that take longer to complete than the time since the first complex animals evolved on Earth. The force is the same. the effect is unimaginably different. There is something in that asymmetry that speaks to the nature of the solar system as a whole. The solar system is not primarily a life-supporting structure. Life is a local accident in an extraordinarily small region of the system's total volume, made possible by the fortunate combination of distance from the Sun, planetary composition, and liquid water that characterizes Earth. The overwhelming majority of the solar system, by volume, by mass count, and by number of objects, exists in conditions completely incompatible with the chemistry we associate with living systems. The Oort Cloud is frozen, dark, radiation blasted on its outermost surfaces, and chemically inert by any biological standard. Life, from the perspective of the solar system's full architecture, is a thin, warm film in the innermost fraction of a percent of a vast, cold, dark sphere. That is not a pessimistic statement. It is an accurate one, and accurately understanding the scale and nature of the system we inhabit is the prerequisite for understanding our own position within it. The Oort Cloud is also a reminder that time operates on scales in the universe that human experience cannot directly access. The objects in the Oort Cloud began their current orbits during the first few 100 million years of the solar system's history. They have been orbiting ever since, through the entire history of life on Earth, through the origin of eukaryotic cells and the Cambrian explosion, and the rise and fall of the dinosaurs, and the emergence of our species, and the entire span of human civilization, without being perturbed significantly from their paths. From the perspective of an Oort Cloud object, Earth's entire history is a brief flicker of activity in a tiny bright region near the center of an otherwise unchanging system of gravitational forces. Continental plates drift, ice ages come and go, entire species evolve and go extinct, mountains rise and erode, oceans rise and fall, and through all of it, the Oort Cloud drifts unchanged in its frozen darkness, perturbed only by the occasional passing star or the slow grinding action of the galactic tide, neither of which cares about anything happening in the warm inner solar system. This perspective does not diminish the significance of Earth's history. It contextualizes it. Life, intelligence, technology, the entire project of human civilization, emerged in a narrow window of time on a small warm planet in the innermost corner of a vast cold structure that has been orbiting the galactic center for 4.5 billion years. The Oort Cloud has been witness to all of it, in the sense that it has been physically present throughout, even if it lacks any mechanism to perceive or record what occurred in the warm, bright region at its center. The science of the Oort Cloud is, at its deepest level, the science of context. It provides the context within which everything else about the solar system is embedded. The planets and their moons and their oceans and their atmospheres and their potential or actual biospheres are all contained within the innermost fraction of a structure that extends light years into the galaxy. That structure is shaped by galactic forces operating on timescales of millions and billions of years. It carries chemical and dynamical information dating to the formation of the solar system. It connects our sun to its stellar neighbors through a web of gravitational influence and occasional material exchange that spans the galaxy. To understand the solar system without understanding the Oort Cloud is to understand a neighborhood. Without knowing the city it sits in, the country that city is part of, or the continent on which that country lies. The planets are the neighborhood, the Oort Cloud is the rest of the map, and the rest of the map is incomparably larger than what most people have ever been shown. That is the Oort Cloud. That is the full story. Not the simplified version that fades to black at Neptune, but the actual version, as complete and honest as the current state of science allows. A sphere of frozen darkness extending more than a light year from the sun in every direction, containing perhaps 1 trillion primordial remnants of the solar system's birth, shaped by the galaxy itself into structures we are only beginning to understand, and connected to the wider universe by flows of matter and gravity that make the concept of a clean solar system boundary a useful fiction rather than a physical reality. You live inside it. You always have. There are some specific numbers embedded in the Oort Cloud story that tend to get lost in the sweep of scale comparisons, but they are worth stating plainly because they carry their own kind of weight. The sun converts 4 million tons of matter into pure energy every second. That rate of energy production has been sustaining the solar system's dynamics for 4.5 billion years. In that time, the sun has lost a significant fraction of its mass to radiation. The solar wind alone has blown roughly 0.1% of the sun's initial mass out into the interstellar medium over the solar system's lifetime. Some of that material passed through the Oort Cloud. Some was captured by it. The Oort Cloud exists in a solar system that has been evolving and changing throughout its history. Not a static structure, but a dynamic one in which every component, from the sun's luminosity to the positions of the giant planets, to the boundaries of the Oort Cloud itself, has changed and continues to change. In 2026, Voyager 1 is approximately 165 astronomical units from Earth. That is roughly 0.17% of the way to the heliopause. Wait, that is the heliopause, not the Oort Cloud. Let us be precise. The heliopause is at roughly 120 astronomical units. Voyager has passed it. The inner edge of the Hills Cloud is at perhaps 2,000 astronomical units. Voyager is about 8% of the way there after 49 years of continuous travel. The outer edge of the Oort Cloud is at roughly 100,000 astronomical units. Voyager has covered about 0.2% of that distance in 49 years. At its current speed, the crossing of the full Oort Cloud would take on the order of 30,000 years. These numbers do not get easier to absorb with repetition. Each time they are stated, they require the same effort of mental adjustment. That is because they are not numbers that any evolved human faculty was designed to handle. Our intuitions were shaped by environments where the longest meaningful distance was the horizon, where the longest meaningful time was a human lifetime, where the most significant structures were mountains and rivers, and the span of a day's travel. The Oort Cloud operates at scales that are 11, 12, 13 orders of magnitude beyond these intuitive baselines. The gap between everyday scale and Oort Cloud scale is not just large, it is larger than the gap between everyday scale and the scale of atoms and molecules. The Oort Cloud is further beyond everyday experience than the quantum world is below it. This is part of why the standard solar system diagram persists despite its radical inaccuracy. A diagram that accurately represented the Oort Cloud at a scale where the planets were visible would require a display larger than any building ever constructed. A diagram that accurately represented the planets at a scale where the Oort Cloud fit on a single page would make every planet invisible. There is no practical way to draw the solar system to scale and show both the planets and the Oort Cloud on the same image. The diagram that ends at Neptune is not just a simplification driven by laziness or ignorance. It is a reflection of a genuine representational impossibility. The human visual system simply cannot process the ratio of scales involved. What science communication can do, and what the best treatments of the Oort Cloud try to do, is provide a series of anchoring comparisons and analogies that allow the mind to build up a sense of the scale, even without being able to visualize it directly. The classroom wall with the period at the center, the basketball sun in one city with the outer boundary in another city on a different continent, Voyager's 30,000-year crossing time, the trillion object population with an average inter-object separation of billions of miles. These are not the same as seeing the Oort Cloud directly, but they are the closest approximation available to human cognition, and they are accurate as far as they go. The scientific literature on the Oort Cloud is extensive and growing. Oort's original 1950 paper in the Bulletin of the Astronomical Institutes of the Netherlands established the basic framework. Jack Hills's 1981 paper introducing the inner cloud region added a critical structural detail. Decades of refinement through increasingly sophisticated computer simulations have improved the models of formation, dynamics, and comet delivery rates. The discovery of Sedna in 2003 provided a concrete physical example of the kind of extreme orbit that the inner cloud is predicted to produce. The detection of Oumuamua in 2017 and Borisov in 2019 demonstrated empirically that material exchange between stellar systems occurs at detectable rates. And the 2025 discovery of spiral structure in supercomputer simulations of the inner Oort Cloud suggested that the galactic tide has shaped the cloud's architecture in ways more complex and more beautiful than the standard models had predicted. Each of these developments is a brick in a structure of knowledge that continues to be built. The Oort Cloud story is not finished. It is a story in progress, being written in real time by researchers at observatories and supercomputing centers and universities around the world, working with instruments both newly operational and still on the drawing board. The next decade of Rubin Observatory operations will add new chapters. The Roman Space Telescope will add others. Future missions, future instruments, future simulations will add more. What will not change is the fundamental fact that the Oort Cloud is there, vast and dark and frozen and ancient, extending more than a light year from the sun, containing within itself a chemical library that preserves the state of the solar system before Earth formed, shaped by the gravity of a galaxy containing hundreds of billions of stars, and still, after 4.5 billion years, sending its members inward as comets that briefly light our sky before retreating back into the darkness. The solar system is not the 8-planet system of the classroom diagram. It never was. It is a sphere of frozen darkness extending light years in every direction, with a small, warm, bright core of planets and moons and asteroids at its center. The core is what we know. The sphere is what we are. You live inside the Oort Cloud. You always have. The solar system was never the neat, compact system of the standard diagram. The standard diagram was always a convenience, a useful approximation, a way of showing the part we could reach and understand while leaving out the part we could not. Now you know about the part we left out. It is most of everything. The Oort Cloud raises a question that seems simple, but turns out to be surprisingly deep. How do we know when we know something? In everyday life, knowing and seeing are closely linked. We trust what we can observe directly. We are appropriately skeptical of things we cannot see. The Oort Cloud sits in an unusual position relative to this everyday epistemology. We cannot see it. We cannot visit it. We cannot even detect its individual members with any current instrument. And yet the scientific community considers its existence as well established as the existence of Neptune or Saturn's rings. The resolution lies in the nature of scientific evidence. Direct observation is one form of evidence, but it is not the only form, and it is not always the most reliable. A well-constructed inference from multiple converging lines of indirect evidence can be more reliable than a single direct observation, which is always subject to instrument error, calibration issues, and the possibility of misidentification. The Oort Cloud is supported by many independent lines of converging evidence, each of which is individually compelling, and all of which point in the same direction. The orbital statistics of long-period comets require a spherical source reservoir at large distances. The galactic tide and stellar perturbations can physically explain how objects at those distances are dislodged and sent inward. Planetary formation models predict that the reservoir must exist with the appropriate total mass. The composition and age of cometary material is consistent with the material having been stored at low temperatures in distant orbits for billions of years. The existence of interstellar visitors like Borisov demonstrates that similar structures exist around other stars. The discovery of Sedna and similar extreme trans-Neptunian objects provides direct evidence of material in the transitional zone between the scattered disk and the inner cloud. Each of these lines of evidence is independent of the others in the sense that they come from different types of observations and different types of analysis. Their convergence on the same conclusion is not easily explained by any alternative model. The probability that all of these independent lines of evidence could simultaneously be consistent with the existence of the Oort Cloud, while the cloud itself does not actually exist, is, for all practical scientific purposes, negligible. This is how science works at its best. Not by demanding direct observation of everything before accepting it as real, but by constructing a coherent picture from multiple types of evidence, and accepting as real anything that is required by a sufficiently robust and consistent body of converging evidence. Dark matter was accepted as real by this standard long before any direct detection. Black holes were accepted as real by this standard long before the Event Horizon Telescope produced the first direct image. The Higgs boson was predicted and accepted as effectively certain before the Large Hadron Collider produced the first direct evidence of its existence. The Oort Cloud belongs in this company. The implications of the Oort Cloud for how we think about interstellar travel deserve consideration as well. In popular discussions of travel to other stars, the distances involved are typically framed in terms of the gap between stellar systems. Alpha Centauri is 4.3 light-years away. Proxima Centauri is 4.2. Getting there requires crossing 4 light-years of essentially empty interstellar space. Any propulsion system capable of closing that gap in a human lifetime would need to achieve a significant fraction of the speed of light, which requires energy densities that no current technology approaches. But this framing ignores the Oort Cloud. Spacecraft leaving the solar system on a trajectory toward Alpha Centauri would not immediately enter empty interstellar space after passing the heliopause at 120 astronomical units. It would still be inside the solar system's gravitational domain for roughly 100,000 more astronomical units, approximately 1.5 light-years, before truly leaving the sun's gravitational influence. It would then traverse about 2.5 to 3 light-years of genuinely interstellar space before entering the gravitational domain of the Alpha Centauri system, which presumably has its own Oort Cloud-like structure extending outward for comparable distances. The journey between stars is not a journey from the heliopause of one system to the heliopause of the other. It is a journey from the outer edge of one Oort cloud to the outer edge of another. The interstellar void that any interstellar mission would need to cross is bounded not by the heliopauses, but by the Hill spheres. And the Hill spheres are separated by only 2 to 3 light-years, not 4. Still an extraordinary distance by any human standard, but meaningfully different from the 4+ light-years that is typically cited. This reframing does not make interstellar travel easier, but it changes the conceptual picture. The space between stars is not a uniform void extending from the heliopause of one system to the heliopause of the next. It is a narrower gap between the Oort clouds of neighboring stars, each of which extends outward to a point where the galaxy takes over from the individual star. The galaxy is not a collection of isolated stellar systems separated by empty space. It is a patchwork of overlapping gravitational domains, each centered on a star, each containing an Oort cloud-like structure, with narrow gaps between them where no star's gravity dominates and the open galaxy prevails. This picture of a galaxy filled with overlapping stellar gravitational domains is not merely a more accurate description of the space between stars. It has implications for the probability of life spreading between stellar systems. If comets and other icy bodies are occasionally exchanged between neighboring Oort clouds through gravitational interactions and interstellar passage, then the same process that delivers organic molecules to planets within a single solar system could, in principle, deliver them between solar systems. The timescales involved are enormous, millions to hundreds of millions of years for a single object to make the transit between clouds. But the solar system is 4.5 billion years old, and countless such transits may have occurred during that time. The panspermia hypothesis, the idea that life or its precursors might spread between planetary systems through space, has generally been considered implausible due to the vast distances and the harsh conditions of interstellar space. The Oort cloud perspective does not make it likely, but it does suggest that the exchange of chemical building blocks between neighboring stellar systems is not as implausible as a simple heliopause to heliopause framing would suggest. Material does cross between stellar systems. We have direct evidence of that from Oumuamua and Borisov. The question is whether any of that material could carry biological or pre-biological chemistry of significance, and that question remains genuinely open. What is not open is the basic physical reality. The solar system is large, much larger than almost anyone who has not specifically studied the question appreciates. Its true boundary, to the extent it has one, lies more than a light year from the sun in every direction. That boundary is not sharp, it is gradual, probabilistic, continuously shifting under the influence of galactic tides and stellar encounters. And within that vast, uncertain boundary drift hundreds of billions to 1 trillion frozen objects that carry within them the chemical record of the solar system's formation, that occasionally fall inward as comets to provide brief and spectacular windows into that ancient chemistry, and that together constitute a structure so large and so old that it challenges every comfortable assumption about what the solar system is and where it ends. That is the full picture, or as close to the full picture as the current state of science allows. The rest, the precise population, the internal spiral structure, the exact outer boundary, the fraction of captured interstellar material, the consequences of Planet 9's existence or absence will be filled in by astronomers working with instruments that are just beginning their surveys or that have not yet been built. The story of the Oort cloud is still being written. What is already written is extraordinary enough. Now you know the Oort cloud, and the solar system will never look quite the same again.